Welcome to another day on the Journey Shake Chem. I can't help myself. I get so excited when we start a new topic and we get to introduce it. Now today's warm-up, you have to change the words to formulas, and the formulas are separated by plus signs. We've had equations of reactions before, so just do the best you can, and we'll talk about them in a moment. It's important to understand that we are changing the words to symbols. And lead metal is just lead. It doesn't matter if it's pellets or powder or whatever it is, it's still just lead. So we have Pb. Plus, it's reacting with, so we use a plus. Silver is +1 and acetate is -1. Therefore, it is just AgC2H3O2. It is important that we remember all the things that we learned in nomenclature because we're going to still be using them. They don't go away. And it produces, or it forms, silver and lead Roman numeral 2 acetate. Well, I know that the Roman numeral 2 means +2 and acetate is -1. Therefore, I must have 2 acetates to get my compound to 0. It's very important that you write the formulas correctly. We have lead, and we need 2 acetate, polyatomic ions. The very first thing you must do is get the formulas correct. If they're not written correctly, then you're going to have a very difficult time balancing those atoms. And as soon as you have a problem balancing, then you might want to go back and double check your charges and make sure your formulas are written correctly. Now, I'm going to look at polyatomic ions as units because they stay together as units most often. And here I have 2 acetate polyatomic ions. Now, I'm going to put a 2 as a coefficient in front because once the formula is written correctly, I can no longer change the formula. If I were to put 2 acetates, then that would be -2 and silver is +1 and the whole thing would be -1, so that wouldn't work. I have to only change what's in front, and I'll give you an example of that when I do the second one. Now that gave me 2 silvers here, so I have to put a 2 in front of this silver so that I have the same number of atoms on both sides of the equation. And now this one is balanced. In the second case, I have iron metal. It's just Fe. And I have oxygen. Well, oxygen, as we recall, is a diatomic molecule. It has 2 of them together when it's by itself. So we always need to remember that. What I would do is on the top of my paper, I would write, I brought clay for our new house. And that would be a reminder to me when I'm writing these equations that when I have something like oxygen, that it's diatomic, and that's the way it needs to be written. Now, oxygen is not diatomic. When it's in a compound like water, there's only 1 oxygen. Therefore, we wouldn't have that in a compound. So iron reacts with the oxygen, and it forms iron 3 oxide. Well, iron is +3. That's what the Roman numeral is telling me. Oxygen is -2. The common multiple between 3 and 2 is 6. There must be 2 irons and 3 oxygens. Fe2O3. In this case, oxygen over here, I have 2 of them. And over here, I have 3 of them. In order to get the same number, I need the common multiple between 2 and 3. And that would be 6. So I'm going to have 2 of these molecules, or formula units, and I need 3 of these. Now, as soon as I did that, that gave me 4 irons, so I can put 4 in front of the iron. Then the number of atoms are balanced. This is very much like, once I write the formula, it's like I have it inside of a box. I have these 2 irons and 3 oxygens. And so when I have the formula written correctly, it's like a closed box that cannot be opened. Therefore, I can only change the number of boxes I have. I cannot change what's in the box. I cannot change the formula, so I must have 2 boxes to get the number of materials or elements that I need. I hope that maybe that makes a little bit more sense to you, and we'll see it again. Well, that's the answer to number 1 and 2. There are a few things that we need to go over together. You have a worksheet that is called the general types of reactions. And there are 5 reactions on there, and you need to take a look at this while you're watching me discuss it. The first type of reaction is a single displacement, and that's the type that we had in number 1 in the warm-up. You have an element plus a compound. We can displace either the positive position or the negative position. If it's a metal, we displace the metal. If it's a non-metal, we displace the non-metal. This next type is double displacement, and we've had those before. When we did an acid plus a base or a salt plus water, there was a double displacement. That is a compound plus a compound. Then we have synthesis, and we've had some of those as well, where we take a acid anhydride and water and we made an acid. That would be a synthesis. Now we're putting it to a general form, and we always get a single product in most cases. Then we have decompositions. Now the decompositions are very important because we are going to reach a point where you will predict the product. And the first one that you're given is a metal hydroxide. So above the hydroxide, I would write -1. And that, a metal with hydroxide, is a base. And when we decompose a base, we get water and a base anhydride. That makes perfect sense. When we have a carbonate, the next one would be a carbonate. Carbonate has a -2 charge. Now, a common molecule that forms when we decompose a carbonate is carbon dioxide. So that makes sense as well. Oxyacids are acids like we've had before, where they are combined with oxygen, like phosphoric, chloric, all those ones that we just had an assessment about. Many of those would be our oxyacids. And again, what do we have to do? I was freaking out about that. Got to find the charge on that non-metal in order to determine which oxyacid that you will get. Those are the types of decompositions, a few of them, and the rest of them you can read through by yourself.